Hello students, today we shall see some examples on eigenvalue problem and finding inverse of a matrix using Cayley-Hamilton theorem, and lastly we shall see similar matrices and one theorem on similarity transform. So first example is find the inverse of the following matrices using Cayley-Hamilton theorem. Applying Cayley-Hamilton theorem, not by verifying Cayley-Hamilton theorem. In the last class we have seen first we have verified Cayley-Hamilton theorem and then we have found the inverse. Now today directly we shall apply Cayley-Hamilton theorem. So for these matrices, first one and third one we shall do, second one will be left as an exercise. So characteristic equation of the matrix A, given matrix A, is determinant of A minus lambda I equal to 0. A minus lambda I means already we know, just we subtract lambda from the diagonal, 1 minus lambda, 1 minus lambda, 2 minus lambda, other things remaining same. So now we expand this determinant in terms of elements of first order letters, because there is 1 0, 1 minus lambda into this into that, minus 1 into 0, so minus 0, then minus 0, then plus 2, plus minus plus, like that. So plus 2 into what, this into that means 2 into 1, minus 0 into that means 0. So now we have simplified this expression and got finally lambda cube minus 4 lambda square plus 5 lambda minus 6 equal to 0. So this is characteristic equation of the matrix. Now by Cayley-Hamilton theorem we know every square matrix satisfies its own characteristic equation, means this lambda we replace by capital A cube minus 4a square plus 5a minus 6i, scalar terms, constant term to be replaced by scalar into unit matrix. This is the definition, actually value of a polynomial expression when the indeterminate symbol is replaced by a square matrix. So minus 6i equal to O. O means here null matrix, 3 by 3 null matrix. Now multiply both sides by A inverse. We want to find A inverse. So in the last class what we have seen, this result we have verified, verification of Cayley-Hamilton theorem. This line we have today directly written, because by Cayley-Hamilton theorem this will be true surely. So this is the application of the theorem. So we have applied. Now we have multiplied both sides by A inverse. Now this A cube we can write A square into A and then A inverse multiplied, A square as A into A inverse multiplied, A into A inverse and I into A inverse. A inverse is I, so everywhere we have taken I and I A inverse. I A inverse is A inverse, and right side O A inverse, null matrix into A inverse is null matrix. Here also A square I minus 4ai plus 5i minus 6a inverse. So A square I is A, ai is A, 5i is there, and 6a inverse I change, it will be 6a inverse. So you have written here first 6a inverse equal to this expression A square minus 4a plus 5i. Now A inverse is 1 by 6 into A square minus 4a plus 5i. Now let us find A square first. A square equal to A into A. So multiplication of a matrix, all of we know. For first matrix we move towards row, for second matrix we move towards column. First into first plus second into second plus third into third. So you are getting 1 here only. And then with second column, if we move with first row, what we get? First into first 0, 0 into 1 0, 2 into 1 2, so we have got 2. Then if we move to third column, first row third column, 1 into 2 2, 0 into 0, 2 into 2, 4 4 2 6, so we have got 6. Similarly with second row, third row we have multiplied, we have got this matrix. Now S square minus 4a plus 5a, let us calculate first. S square minus 4a plus 5a, this is S square, we have got the value here substituted, and 4a, this is A, multiply every element by 4, we have got this, and 5i means diagonal 5 5 5, unit matrix 1 1 1, so it is 5 by 5 5 5. Now we have calculated this matrix minus that plus that, so as usual we have subtracted and added, and finally we have got this matrix. Therefore A inverse will be 1 by 6 of this matrix expression, and that is 1 by 6 into this matrix, 6 1 by 6 taken inside. So we have got the inverse using Cayley-Hamilton theorem without verifying it. without finding adjoint matrix, cofactors, etc. We have found the inverse of the matrix. Now Roman 3. Characteristic equation of the given matrix capital A is, capital A was 4 by 4 matrix. From diagonal we have subtracted lambda and all the diagonal elements are 0. So it will be minus lambda, minus lambda, minus lambda like that. So other elements remaining same. So this is the determinant of A minus lambda I equal to 0. Now we expand this 4 by 4 determinant minus lambda into this line, if we omit, so this part remains. So this is the determinant, lower order determinant, third order determinant here, then minus 1 into here minus 1, so minus, then if we omit for second part, we omit this row and this column, so what we get, 0 0 1, 1 minus lambda 0, 0 1 minus lambda, it is there, and rest two elements are 0. So this is the expansion of the determinant. Now again we expand this determinant, two zeros are here, so it will be only just minus lambda into minus lambda into minus lambda minus 0. These two elements are 0, so only this part, and for this 0 0 1, so only 1 into 1 minus 0, so 1 minus 0. So finally we have got lambda to the power 4 square, and here also minus 1 square, so it will be just lambda to the power 4 minus 1 equal to 0. This is the characteristic equation. Therefore, by Cayley-Hamilton theorem, we get a to the power 4 minus 1i. 1i means it is only i equal to O, null matrix. Every square matrix satisfies its characteristic equation. Here, characteristic equation is simple. Lambda to the power 4 minus 1, 0. So, we have got a to the power 4 minus i equal to O, means a to the power 4 equal to i. Now, if we multiply by A inverse into a to the power 4 equal to A inverse into I, rather pre-multiplied. So, a to the power 4 is a cube into A into a cube we can write. So A inverse will be I, means it will be only a cube, and then A inverse into I is A inverse. So what we have got, A inverse equal to a cube. So we are only to find a cube. So first we find A square, A into A. So as usual we have multiplied within this process, row column process, first into first plus second into second plus third into third plus fourth into fourth, and put the value here. So you have got A square, this matrix, and then A inverse is a cube. So A inverse equal to a cube means A into a square, or you can write a square into A. We have written here A into a square. So again we have multiplied as usual in this process, row column, and got this matrix. So this is inverse of the matrix, 4 by 4 matrix, using Cayley-Hamilton theorem, without finding adjoint, without finding cofactors, etc. Easily obtained. Next, some theoretical examples, the results on eigenvalue. If lambda is an eigenvalue of a non-singular matrix A, then prove that lambda inverse is an eigenvalue of A inverse. Lambda is an eigenvalue of a square matrix A, but square matrix A is non-singular. Then we have to prove lambda inverse is an eigenvalue of A inverse. First we shall prove, of course, lambda is non-zero. So lambda is an eigenvalue of A, means Ax equal to lambda x by definition for some non-zero column vector x. Now we have to prove first lambda not zero, because lambda inverse is an eigenvalue of A inverse we want to prove. So if lambda 0, what happens? Let us see. If lambda 0, then Ax equal to 0x. 0x is O, 0 vector, 0 column vector rather. So x equal to A inverse O means 0 vector. Capital X is 0 vector. We have multiplied by A inverse because A is non-singular, A inverse exists. So what we have got, x, capital X is 0 vector, but what is the comment? X is a non-zero column vector. Ax equal to lambda x. If lambda is an eigenvalue, then x is a non-zero column vector. Here we have got 0. If we take lambda 0, we get capital X 0 vector, which is contradiction. Therefore, lambda not 0. So lambda inverse exists, non-zero scalar. Now Ax equal to lambda x we have, and then we multiply both sides by A inverse. A inverse Ax equal to A inverse lambda x. And matrix multiplication is associative, so you can take A inverse A in one bracket. That will be Ix. Ix will be again x. And here also lambda is scalar, be taken out. Lambda A inverse x. So what we have got, this lambda if we take here, it will be 1 by lambda, means lambda inverse. So Ix is x. So finally lambda inverse Ix is x here, lambda becomes here, so it will be lambda inverse A inverse x equal to lambda inverse x. A inverse x equal to lambda inverse x, where capital X is a non-zero column vector. That means what? This result, this line says that yes, lambda inverse is an eigenvalue of A inverse by definition. So we have proved if lambda is an eigenvalue of A, lambda inverse is an eigenvalue of A inverse. Now one observation, lambda is an eigenvalue of A inverse implies lambda inverse is, lambda is an eigenvalue of A, not A inverse. Lambda is an eigenvalue of A inverse implies lambda inverse is an eigenvalue of A. So this is wrong. This is A. Lambda is an eigenvalue of A implies lambda inverse is an eigenvalue of A inverse. We have just proved. Therefore, if we write alpha is an eigenvalue of A inverse, then alpha inverse is an eigenvalue of A inverse inverse. But A inverse inverse is A. So what we have seen, if inverses of eigenvalues of A inverse are eigenvalues of A again, reverse is also true. So it follows that eigenvalues of A inverse are exactly the inverses of the eigenvalues of capital A. So the result is proved. Next, prove that 0 is an eigenvalue of a square matrix A if and only if capital A is singular. What we have seen in the previous result, if A is non-singular, then 0 cannot be eigenvalue. 0 cannot be eigenvalue. Okay, so that is as a result we have stated here. Now 0 is an eigenvalue of capital A implies and implied by if and only if determinant of A minus 0i equal to 0. Determinant of A minus 0i, lambda is 0 here, but 0i is O, null matrix. Every element of I is multiplied by 0 means it will be null matrix. So determinant of A minus O is A, determinant of A equal to 0. Therefore A is singular. So 0 is an eigenvalue of A if and only if A is singular. We have proved. This is both way true. Now next example, prove that two eigenvectors of a square matrix A corresponding to two distinct eigenvalues of A are linearly independent. Eigenvectors corresponding to two distinct eigenvalues of a square matrix are linearly independent. So let us see the proof. Let capital A is a square matrix of order n and capital X1 and X2 are two eigenvectors of A corresponding to distinct eigenvalues lambda 1 and lambda 2. Therefore, by definition, Ax1 equal to lambda 1 x1, Ax2 equal to lambda 2 x2 for some non-zero column vectors capital X1 and X2 in R to the power n. Now we have to prove that this capital X1 and X2 are linearly independent. So let the linear combination alpha 1 x1 plus alpha 2 x2 equal to 0. Here it is 0 means 0 vector, where alpha and alpha 2 are scalars means real numbers. So multiply both sides by A. So matrix multiplication is distributive. Right side A into 0 vector is 0 vector, and alpha 1 is scalar, can be taken out. Alpha 1 ax1 plus alpha 2 ax2 equal to 0 vector. Now ax1 is lambda 1 x1, ax2 is lambda 2 x2. So what you get, and scalars alpha 1 lambda 1, this two scalars can be taken in one bracket. So alpha 1 lambda 1 x1 plus alpha 2 lambda 2 x2 equal to 0 vector. This is line number 2. Now pre-multiplying number 1 by lambda 2 we get, see this is real number 1. If we multiply it by lambda 1, pre-multiplying number 1 by lambda 2, so it will be lambda 2 alpha 1 lambda 2 alpha 2 x2. Okay, so you have got lambda 2 alpha 1 x1 plus lambda 2 alpha 2 x2 equal to lambda 2 into 0 vector here. So lambda 1 lambda 2 and alpha 1, this can be interchanged in position because they are scalars. So it is alpha 1 lambda 2 you have written here, also alpha 2 lambda 2 you have written, and then right side is 0, scalar into 0 vector is 0 vector. So now if we subtract 2 from 3, 3 minus 2 means this alpha 2, this alpha 2 lambda 2 term and this alpha 2 lambda 2 term will be cancelled. So what you get, alpha 1 lambda 2 x1 minus alpha 1 lambda 1 x1 means alpha 1 into lambda 1 minus lambda 2 x1 equal to 0 vector, implies alpha 1 into lambda 1 minus lambda 2 is equal to 0. This is 0 scalar because capital X1 is a non-zero vector. So if product of a scalar and a vector is 0 vector, then either scalar is 0 or vector is 0. That result we have used here. Capital X1 is a non-zero vector, so the coefficient scalar should be 0. Now lambda 1 not equal to lambda 2 because they are distinct, therefore alpha 1 must be equal to 0. So therefore number 1 becomes alpha 2 x2 equal to 0 vector. It was alpha 1 x1 plus alpha 2 x2, but alpha 1 x1 is 0, so alpha 2 x2 becomes 0 vector. And from this we can get alpha 2 0 because capital X2 is a non-zero vector. So what we have got, the linear combination alpha 1 x1 plus alpha 2 x2 equal to 0 vector implies both alpha 1 and alpha 2 are 0 scalars. And this says that yes, capital X1 and capital X2 are linearly independent. And this result we have proved for 2 vectors. Actually it is true for n vectors also, general case. So this is stated as a theorem. The eigenvectors or characteristic vectors, as you call, v1 v2 dot dot vn, corresponding to distinct eigenvalues lambda 1 lambda 2 dot dot lambda n of a square matrix capital A are linearly independent. Example next. This is also a theoretical example, another standard result. If lambda is an eigenvalue of a square matrix capital A, then prove that g of lambda is an eigenvalue of g of capital A, where g is a polynomial. G is a polynomial. So let g lambda equal to a naught plus a1 lambda plus a2 lambda square plus dot 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 a n lambda to the power n is a polynomial in lambda of degree n, where a naught, a1, a2 dot dot n are constants. Lambda is a scalar indeterminate. So this is a polynomial in lambda of degree n. Now therefore g of a, if we replace lambda by a, we have to replace this a naught by a naught into capital I. This is the definition of value of a polynomial for when the indeterminate symbol is replaced by matrix, square matrix. So g of a equal to this expression. Okay, where is the unit matrix of same order as that of A. Now lambda is an eigenvalue of A implies Ax equal to lambda x for some non-zero column vector x. Definition. Now let us pre-multiply both sides by A. Matrix multiplication is associative, so A into Ax equal to lambda can be taken out, scalar lambda Ax. But A is a square x and lambda Ax. Ax is lambda x, we know. So this lambda again becomes lambda square. So what we have proved, S square x equal to lambda square x means from this line we can say that lambda square is an eigenvalue of capital S square. Again we pre-multiply by capital A as usual, and using this line we get what, a cube x equal to lambda cube x. So from this line we can say that lambda cube is an eigenvalue of a cube. In general, a to the power nx equal to lambda to the power nx means lambda to the power n is an eigenvalue of a to the power n for all n 1 2 3 dot dot n, anything. Okay, therefore g of ax equal to, this is ga value and this is capital X, multiply by capital X, and then ix is x, ax is lambda x, s square x is lambda square x, a to the power nx is lambda to the power nx. We have proved. So what we have got, again take x common, it is g of lambda. So what we have proved, g of a into x, ga into x equal to g lambda into x, where x is a non-zero column vector, therefore g lambda is an eigenvalue of g of capital A. This is proved. Now we define what are similar matrices and similarity transformation. A square matrix A cap of order n is said to be similar to another square matrix A of same order n if there exists a non-singular square matrix capital P of order n such that A cap equal to P inverse AP. A cap equal to P inverse AP. A cap is similar to A if there is a non-singular square matrix P such that A cap is equal to P inverse into A into P. Or of course you can write A cap equal to PA P inverse also, PA P inverse. Whether the first one is with inverse or last one is with inverse, all the same, because here if we replace P by Q, say P inverse, this P inverse equal to, if I put Q, and then automatically P will become Q inverse, that is Q inverse AQ. And if P is non-singular, P inverse is also non-singular, so the result can be written as Q inverse AQ, where Q equal to P inverse. So both are definition. Of course we shall use this one mainly. So similarity transform, this transform of a matrix A by a non-singular matrix P to A cap means A becomes A cap when pre-multiplied by P inverse, and post multiplied by p, where p is a non-singular square matrix of same order as that of A. And this transform of A cap to A to A cap is called a similarity transformation. Transformation of A to A cap by this operation, A cap equal to P inverse AP. This transformation is called similarity transformation. Now another result, standard result. Similar matrices have same characteristic polynomials. Same characteristic polynomial. So let A and B are two similar matrices. Instead of A cap, I have written here A. That is, A and B are square matrices of same order, and there exists a non-singular matrix P such that B equal to P inverse AP, because A and B are similar. Now characteristic polynomial of B is determinant of B minus lambda I. Value of B is P inverse AP, and I we can write as P inverse P. Again, between P inverse and P we can write another I, because IP equal to P. Now we take P inverse common from the left and P common from the right. So what you get? P inverse into A minus lambda I into P and under determinant. Now properties of determinant, if we use three determinants, you can write determinant of P inverse, determinant of A minus lambda I, determinant of P. And this determinant of P inverse we know 1 by determinant of P. And this 1 by determinant of P and this determinant of P gets cancelled. So what you get? Determinant of A minus lambda I. But this is characteristic polynomial of A. So A and B are similar. They have same characteristic polynomial. Therefore, they will have same characteristic equation, and therefore they will have same characteristic roots also. That is eigenvalues. So it follows that similar matrices have the same characteristic equation and hence have the same characteristic roots or eigenvalues. So another result, standard result, involving eigenvectors also. Here we have proved eigenvalues for an eigenvalues only. Here this result is involving eigenvectors also. If A cap is a square matrix of order n which is similar to another square matrix A of order n, then A cap has same eigenvalues as that of A. This we have already proved here, of course. Further, second part is further, if capital X is an eigenvector of A, then P inverse X, let us name it Y. Y equal to P inverse X is an eigenvalue vector of A cap. And what is A cap? A cap is P inverse AP, corresponding to the same eigenvalue. So let us see the proof. Let the matrix A cap of order n is similar to the square matrix A of order n, then there exists a non-singular square matrix P of order n such that A cap equal to P inverse AP. This is definition. Now let lambda is any eigenvalue of A and capital X non-zero, not equal to 0, be the corresponding eigenvector, then AX equal to lambda X. Definition. Let us pre-multiply by P inverse both sides. Then this A we can write as AI also. Okay, and this lambda can be taken out, scalar, first position. Now this I we can write as P inverse. Okay, now this P inverse AP is A cap. Okay, and this P inverse X let us name as Y. Here we have named. So A cap Y equal to lambda Y, because this is again Y. So A cap Y equal to lambda Y. Now if you can justify that capital Y is a non-zero column vector, then yes, lambda will be an eigenvalue of A cap. So let us see what happens if Y is 0 vector. If Y equal to 0, then what you get? P inverse X equal to 0 vector. Now multiply by P both sides, P inverse P into 0 vector. P inverse is Ix is X. So what you get? P into 0 vector is 0 vector. So X equal to 0, a contradiction, because capital X is a non-zero column vector. So if Y 0, then X becomes 0, a contradiction. That means what? That means Y not 0. Therefore Y not equal to 0 vector. So this result, A cap Y is equal to lambda Y, implies that lambda is an eigenvalue of A cap, and P inverse X means Y. This Y means P inverse X. Y equal to P inverse X is the corresponding eigenvector of A cap. So the result is proved, and examples on this we shall do in the next lecture. Thank you.